Bless you. Oh, there we go. Kim.
That was solid.
Kim the Sneeze Lucero. Okay. So let's get started today, and we are shifting gears big time today and this week. We have our first test of the market period coming up on Friday. We have a lesson today in sequences. Tomorrow we'll have a second lesson in sequences. And then on Wednesday and Thursday, pre-tests. Friday, test. This is a huge, huge week. You're only getting 2 tests this market period, I believe. That's less than ideally I would like to give, but it's the way the cookie crumbles. Next market period, you'll have a whole lot of them. Yes?
Do you watermark your photos when you put them up?
Sometimes I do and sometimes I don't. So, I know that if anybody hires me to do a shoot with their animals, they're going to get very, very large files that you can blow up to like the size of this screen with no problem. If you take them off the internet, they're not as good. They're not as crisp, and yeah, it's not the same quality. So some people could do it, but what I figured I would charge, I found people in New York City who charge $975 for 2 hours of taking pictures of pets.
That's a lot.
It is, and I looked at the quality of the pictures. I found basically 4 or 5 photographers on Long Island that take pictures of pets, and 2 of them were no good. One of them was outstanding. And when you say that, you have to be really careful, because all you're seeing is their best pictures. If someone wanted to look at my 10 best pictures, the 10 best pictures are awesome. But I think you also have to look at all the ones you don't print and don't put up there. And the other 2 were very good.
You're like the photographers from that one episode of iCarly when they set up their
Oh my God, yeah!
Well,
and then they had the cat, and then Sam stole the cat, and then Freddie shaved it, and then the guys who were the photographers, they freaked out and they started eating blue tea.
Drinking.
I don't know anything about what you just said, but that's okay.
It was a great episode.
Okay,
They
that's
had a
wonderful.
hole in the photography market. They vandalized the photography studio. It was a mess.
I will be really, really happy if I just get $375 or $350 for 2 hours worth of work. And it's really more than that, because you have to drive out, you have to drive back, and then you have to process the pictures. Processing the pictures can take quite a long time. And then the prices are gonna go up after a while. So for now, they're pretty good. Plus I have a half-price sale on the first 5 packages I sell. And then the next 5, I'm gonna do a quarter price. And we have a guy who gives Bauer monthly massages, because he's got these issues. So anyway, long and short of it is, this is the guy who massages all the racehorses at Belmont Racetrack. And he does Jimmy Buffett's dogs, he does a lot of really famous dogs in the Hamptons. And he constantly has people asking him to take pictures of the animals they have. So he thinks he can get me in there. He's also buying a zebra puppy. He thinks he can get me in to take pictures at all the horse shows in the Hamptons and stuff during the summertime. Hired by people to go out and shoot their animals with camera, obviously, for the day. And assuming that gets done, each day out there is like $1,000 in the back pocket, plus connections.
The people in the Hamptons are rich.
Yes, they are.
So that's a thing.
So it's a good deal, and I do it because I want toys. I really like my toys, and I can't afford my toys if I don't make extra money. So toys is also known as camera equipment. My camera body started $6,000, and my camera lenses started close to $3,000. What's that?
I thought you were talking about
No. Okay. Ready? Here we go. Let's push forward and get this last topic out of the way for the test that we're going to take on Friday. Mrs. Rosenblatt gave her students what she thought was a pretty simple task. What's the next number in the sequence? 2, 4, 6, 8. Cody, I'm thinking it's a +2 pattern, so it continues 10, 12, 14, 16. Allie, I'm thinking it's a repeating pattern, so it goes 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, so on. And Suri, I am thinking of the units digit in the multiples of 2, so it continues 2, 4, 6, 8, 0, 2, 4, 6, 8, 0. In other words, she just looks at the unit digit, oh, over here, the units digit. Okay, Anthony?
Yes, yes.
Yes, they are valid responses, very good, okay. What's the 100th number in the sequence using Cody's scenario? Anthony?
200.
No.
Oh, I got 200.
I got 200.
Oh, hold it, I'm sorry, I was looking at the wrong one. Yes, Cody's would be
200.
2 times 100 term, yes, okay, good. And what's the next one here? What is the expression in terms of, I guess that says n for the nth number in Cody's sequence?
2n.
2n, very good. Because in Cody's sequence, it's like you take the first term, second term, third term, multiply them all by 2 to get them out there. Yes?
There's more to the second question.
Is there?
As for each of them.
Oh, alleys and Surreys. What's the 100th number in alleys? What would that one be?
4.
8.
8. Yeah, I got.
Look, 2, 4, 6, 8, 2, 4, 6, 8. So every fourth term is 8, right?
Oh.
So if every fourth term is 8, 4 goes into 200 evenly. So the 200th term will be one of the fourth terms. Therefore, it has to be 8. And Surrey's
Oh my god. It's 0.
is 0 because the fifth term is 0, and that divides into 400, the fifth term in the repetition. Okay, any questions?
What was the third
All
one?
right, so
0.
0. What we're trying to do is we're trying to get you to realize that sometimes there's more than one way to look at a sequence, and that you're not limited by one way only as long as the sequence makes sense. All right, so Jerry has thought of a pattern that shows powers of 2. Here are the first 6 numbers of Jerry's sequence. 1, 2, 4, 8, 16, 32. Write an expression for the nth number. Go ahead.
The N. Don't ask me what it means.
That means for any general term. Sorry?
N times 2.
Well, let's try it. Here's the fifth term right here. If I do 5 times 2, do I get 16? No. Go ahead.
2 up n minus 1.
Yes, 2 to the n minus 1. Now, let's talk about the difference in these patterns. Before we had a pattern that looked like this. 2, 4, 6, 8, 10, 11, blah, blah, 10, 12, I'm sorry. Blah, blah, blah. I was going up by 2s. And what we said was that the answer was 2n in terms of a way to represent that. So notice, I'm adding 2, yet I represent it as multiplication. Here, I'm multiplying by 2, and the correct answer is 2 to the n minus 1. It's because what you're doing is, you are, in multiplying by 2, that's exponentiation, isn't that? Like, if I do repeated multiplication of 5, that's like 5 to some exponent. So if I repeatedly multiply by 2, that is 2 to some exponent. Now, it has to be n minus 1 because the first term is 1, and the way to get 1 is 2 to the 0. So I have to do 1 minus 1 to get 0. So I have to include the negative 1 when I get to that particular representation. Okay? All right. Now, that's some general ideas just designed to get you to start thinking about sequences. Now, we're going to take those sequences and we're going to formalize it and put a little bit of discipline on it. But that said, I also like to just kind of think this through and not be so top down in our learning. I like to struggle a little bit and kind of have it make sense to us, because then these formulas carry more impact. Show you what I mean. Example, 3, 7, 11, 15, 19. These are all what we call arithmetic sequences. My experience is that kids will mispronounce arithmetic all the time because they've spent most of their life saying arithmetic. So everybody say arithmetic. Arithmetic, very good. Okay, so arithmetic means that you add or subtract, because subtract is just adding a negative, the same number over and over and over again every time. For example, in this case, you're adding 4s every single time, okay? That's an example of an arithmetic sequence. What would the 7th term be?
23.
AJ? 27 is right. Okay? God bless you. I have a question now. What would be the 35th term? What would be the 35th term? Anybody think they got it?
Nope.
Spencer?
Is it 248?
I don't think so.
135.
No.
Dang it.
95? No.
Wait, it's
You're closest, so maybe I did it wrong in my head. Let me just do this very quickly. 4,
Is it one?
hold it, shh, 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 shh. Hold it, maybe, let me see. Hold it, shh, shh, I need to think.
248.
No, you're not closest. What did you say it was, AJ?
35.
No,
I got
it's not.
140.
I got 140 also.
140.
35 times 40 equals
Okay, now, let me go back for a second. Let me go a little bit to the history of mathematics here. And this little kid by the name of Frederick Gauss, sitting in a classroom,
Oh, I know him.
there you go, he was alive in the 1800s.
He invented the division symbol, right?
Yes. Frederick Gauss, sitting around in his classroom way back when, the teacher turns around and gives some busy work because his teacher's absent, so the teacher leaves some work for him to do. He's in 3rd grade, I think, maybe 2nd grade. And the teacher says this, I want you to add the following numbers. Wait, plus 97. Let's also make this a 96. So that's what the teacher says. She says, I want you to add the first 100 numbers. So little Frederick's sitting in his seat, he's hanging out. After about 15 seconds, he walks up to the teacher and he says, I got it, it's 5,050. Might have even taken 10 seconds, 5 seconds.
What's he supposed to do? I'm confused.
You're supposed to add up all the numbers, 1 plus 2 plus 3 plus 4 plus 5,
Oh.
add them all up to 100. Took him less than 15 seconds, might have taken him 5 seconds, the kid was so fast. So the teacher looks at him and goes, no way. You didn't do that, you're just handing in the work so you don't have work to do. Right, the kid wouldn't do that. So Frederick goes back to his desk, sits down, comes up and goes, oh, I'm quite sure I'm right. Teacher says, all right, tell me, how did you add them that fast? 1 and 2 is 3, 3 and 3 is 6, 6 and 4 is 10. And she goes, no, why would you do it that way? He says, what's 1 plus 100?
101.
What's 99 plus 2?
101. Wait, why did you do it like that?
What's 3 and 98?
101.
What's 4 and 97?
That's 100.
How many pairs are there?
49.
No.
50.
50. So he does 100 times 50, 5,050. That's it, I'm
How
done.
does a little kid think that?
Right? Well, he also went on to become one of the greatest math geniuses in the history of the world. He's really sharp.
Wait, why did you do it like that? He could have just done 1 times 99 times 49 is 4,900 plus 100 plus 50.
I lost you.
No.
That's all I
That's so much easier because you're doing 101 and that's just confusing.
Spencer, it's the
No,
next one.
multiplying by 101 shouldn't be confusing. So anyway, here's my point. My point is, sometimes it helps to see
Wait,
into
hold on. It's only
the sequence. What?
why'd you write 100?
What?
It's in
Oh, I wrote 100, it should have been 101.
Yeah.
Okay,
100's easier.
so,
Yeah, it's so good fun.
now, what I want to do is take that idea and look at what's happening here. What am I going up by? I'm going up by 4. So if I go to the 35th term, careful now, how many times have I gone up by 4?
Oh,
No.
you're going up by 4. I was going up by 7.
Down. How many times am I going up by 4? 34 times. Because you don't go up by 4 to get to the first term. Only after that do you go up by 4s. So I take the first term, namely 3, and then I do 34 times 4. Because I'm adding 4 34 times, agree? And then I add whatever that first term is. So 34 times 4 is 120, 136, 136 and 3 is 139. So that's what it adds up to.
Hey, I was 4
Wait.
off.
Okay,
So it's not 140?
no, I guess it's 139. Now, this is, yes,
So if you did start by going up by fours, it'd be 35, you wouldn't have to add the first number?
you can't start by going up by fours because the very first term is 3 and you do not add to get to the first term. So if you carry it out a step further, a way to look at this is, it's the first term plus 4 times n minus 1, where n would be if you want the 35th term. If I wanted the 100th term, it would be 100 minus 1. If I wanted the 50th term, it would be 50 minus 1. Does that make sense?
Yeah.
Okay, let's apply that to the next one. What is the 35th term of the next one? You do have your calculator, so this should be pretty easy. Spencer apparently is looking for redemption.
Is it negative 63?
Let me see.
Yeah.
My pattern is that I'm going down by 2s, right? How many times am I going to go down by 2?
34 times.
34, so I get 34 times negative 2, and then I'm starting at 5. So yes, negative 63 would be the correct answer. Now, let's show you by putting it into the formula. First term is 5, I did that. Common difference is negative 2, so I did that instead of the 4. And 35 minus 1 is 34. Bless you. Now, very important. We have some terminology here. You see how I wrote first term here? There's a way that we write first term. Mathematicians are two things. They are brilliant and they are lazy. They do not want to write 1, 2, 3, 4, 5, 6, 7 symbols. So they just write a sub 0. Do you ever hear of, like, with a disease, patient 0? You heard of that, right? Patient 0 means the first infected person. So if you were to get some disease that started sweeping across a particular area, the Center for Disease Control will try to trace that disease back to the first infected person. And they call it, yes, in the Bacon household this year, we've had a number of patient zeros. Who was the patient 0 when the flu ripped through your household? You?
Me.
All right, so Sydney was patient 0.
She's patient zero for everything.
What's that?
I said she's patient zero.
She's patient 0 for everything, it
Yeah.
always goes from you? Okay. Well, what we do is instead of saying patient 0, we say a sub 0. And all it means is the very first term in the sequence. So in this case, example 1, a sub 0 is 3. Sub is short for subscript, right? You know, superscript is like an exponent, subscript's below. And 5 is my a sub 0 here. Now, those are examples of arithmetic sequences where you add the same thing over and over and over again. A geometric sequence does not add, it multiplies or divides. First off, what's a sub 0 here? 5. Good. With this, what you're going to do is you're going to constantly come across a very similar formula. Here we had n minus 1. It's going to be the exponential like we did before, except the exponent's going to be n minus 1, not n. Remember we did a times b to the x earlier in the year, and we graphed exponential functions that look like this when we graph them? Okay? This has to be n minus 1 because, again, the first term I'm not going to multiply yet. The first term I'm not multiplying to get. But what do I multiply after that? To go from 5 to 10, what do I multiply by? 2. 10 to 20. 2. 20 to 40. 2. So if it wants the 7th term, what I'm going to do is the first term, a sub 0, which is 5, times 2 to the 6th. Always subtracting off that 1. On your calculator, do 5 times 2 to the 6th. Remember, use the up arrow symbol. Okay, 2 to the 6th is 64 times that, 320? 320?
I didn't even have to do that.
What's that?
I didn't even have to do that.
Yeah, you could keep doubling it, right? Here's the thing, and this is the reason why I did the 35th term ones here. If I say what's the 7th term, you could just write out the pattern. If I say what's the 35th term, it's gonna take you quite a while to do it, particularly if I give you a geometric, then it's gonna get ugly. So it's much quicker to use the formula when the term is a high number term. When it's a low number term, then it's not such a bad deal. Okay, God bless. So far, what we've talked about is a couple of different things. We have talked about the idea that there are arithmetic sequences and geometric sequences. What's the difference between an arithmetic sequence and a geometric sequence?
Arithmetic is, you add or subtract by something.
That's right. And what is a geometric? Everybody? Multiply or divide. Very good. In both cases, it is extremely important that you realize in the formula it's not n, God bless, it is n minus 1. Why is it always n minus 1 and not n? It's important that you realize why it's n minus 1 and not n. Mr. Egan?
Because of the a sub 0.
That's right. You don't need to add up to or multiply up to or divide the first term. So a sub 0, also known as the first term, you don't need to do the operation to. It's only after the first term. Since it's after the first term, we are sure to include a minus 1. Okay, so far so good? All right, let's start ripping through some more work now. And we have 2 days of going over this, not just one. Okay, consider the sequence that follows, the +3 pattern. Write a formula for the sequence using both a sub n notation and f of n notation. Let me just show you how to do this. It's not hard, it's very similar to what we've already done. One is to say a sub n equals the first term, which is 4, plus 3 times n minus 1, and the other one is f of n is 4 plus 3 times n minus 1. God bless. So we always write what the first term is, and then we take the common difference and multiply it by n minus 1. Make sense? Okay, here's the thing. I want you to know that there really is another answer. The other answer could be found by looking at things slightly differently, which we'll do over time. But let's do a little algebra here. Can't I distribute the 3? And then I would get 4 plus 3n minus 3, which is 1 plus 3n. So if you wrote 1 plus 3n, that's also worth full credit. Either one of those would be acceptable. The reason some people say 1 plus 3n is they say, well, let me make it like y equals mx plus b, and this is the first term. Well, the 0th term is like the y-intercept, so if I go back 3, I would get 1, and this would be like my b for y-intercept, and my rate of change is the slope, and in this case, that's positive 3. So they'll look at it as the y-intercept is 1, plus the rate of change is 3. So usually, we write it this way, but it's important for you to understand that the two answers are equivalent, okay? Now, does the formula f of n equals 3 times n minus 1 plus 4 generate the same sequence? Why might some people prefer this formula? This is actually the formula we prefer. They were probably looking for the 1 plus 3n formula, okay? Now, we can put all of that together by graphing the pairs. Now, we just did the pairs going this way. First term, second term, third term, fourth term. And what was the first term in that sequence that they listed? 4, then it was 7, 10, 13.
Yep.
So 1, 4, then we go up to 7, then we go up to 10, then we go up to 13 and 16. And if you look at this, do you see how we get, if I start at 1, if I just go backwards here, if we start, I'm sorry, at 4, if I go backwards here, I get my b or my y-intercept, and how the two formulas really are the same. The formula that I prefer, the one with the n minus 1, shows where we begin with the first term, and the other formula shows if we were to think of it as a line with y equals mx plus b. Okay? Questions? Consider a sequence with a -5 patterns. Write a formula for the nth term. Go ahead. God bless. So the nth term would be something like a sub n or f of n, either one, it doesn't matter, equals 30 minus 5 times n plus 1. Agree? Everybody with me on that? Yes. Because the first term is 30. It's always a sub 0. First term, the common difference is negative 5, right? So there's my common difference, and then it's always n plus 1. What would the value of the 20th term be? Just put 20 into the equation. What's 20 plus 1? What's 21 times negative 5?
105.
Negative 105, which altogether is negative 75. So that would be the 20th term. Any questions? All right, we could graph, we would get like a graph we did before. Next one, very quickly, I want to do a geometric sequence before we leave. Here's the times 5 pattern. Write a formula for the nth term. So that would be a sub n or f of n equals, it doesn't matter. What's the first number? 1 times, what's the common ratio? 5 to the n minus 1. That's my answer. Okay, for the 10th term, you plug in a 10. Hasta la vista, vaya con Dios, toodaloo, ta-ta, arrivederci. Smile a lot. Ciao, arrivederci, adios, amigos, y amigas. Gurushrus, Gaddafish, yo, have fun.